Again. Okay, so first off, I want to let you guys know I decided to go ahead and move the exam back, the midterm from next Thursday, from a week from today, to actually the Tuesday thereafter. So I think it's 13 days from now. I do have two versions, and I'm getting ready to have a third version of the practice test up there. So one of them's called practice midterm, the other one's called respondus practice midterm. The third one's going to be respondus video practice midterm, because if you guys have a camera, I don't know. I got to talk to Miss Raskovic. I'm not sure if she wants to sacrifice her time to do my midterm. And if that's the case, I might just get y'all to do it on your own camera if you have a camera. So that's the next question. Does everybody here have a camera connected to your computer, an internet cam of some sort? Yes. Yeah. Okay. At least y'all three do. That's cool. So I'll set it up that way just in case, and then you just be able to take it from the luxury of your house or whatever, and you can take it on Tuesday during the class time if you want. We're going to try to everybody take it at the same time, so nobody has any advantage. If you start, a couple minutes late or a couple minutes early, it's not going to be a big deal. I want you to have a full 75 minutes. I might even give you a full 2 hours if you want. But the main thing is I'll let you know that beforehand. But by having the video, basically Respondus has people that watch you, and I can actually log in as well and see you while you're taking your test. And what they'll do is they'll have you hold up a photo ID next to your face. You can cover up like if it's your driver's license number or something like that, you might not want everybody to see that. And that's understandable. So you don't have to show me that part. But I do need to see your name on the ID, your face, and then the face that's on the ID. You also show each of your pages of scrap paper or your equation sheet, because remember, your equation sheet's allowed to use all the equations that are numbered in your book, plus a couple of those that I made up, like the Biot-Savart law, the way I made that up, and the way I made up the integral form of Coulomb's law. So you can include those even though they're not even in your book. And you can also put any tables of integrals in there, any tables of derivatives, any trig identities, any of that stuff, and any constants that you want. I don't care if you have those. If you feel the need to put a name for the variables, that's okay, but I don't want any full sentences, and I don't want strings of equations that are sort of working out examples, because that could be obviously a problem. But you do have now basically a week and then 5 days. So got another person coming in. Oh, Sean Murphy's logged in twice. All right, so that's coming up. Last time we got through most of Ampere's law. I wanted to do a toroid for you, and I'm going to do another problem, and I'm going to do something that's a little different from what's in the textbook. The textbook has a typical problem, and I worked this for my lecture class. So not only that, it's also solved in one of my past videos, so everybody can see the video of the one from the lecture, from the class, or from the textbook. And that's pretty well explained. I don't like the way they do it, but it's pretty well explained. No, that one I do like the way they do it. It's fine. I was thinking the Biot-Savart one. But anyways, I'm going to do one a couple levels higher, just to give you an idea of how it could be. So what they did was they imagined a really long wire carrying a current I and a radius R, but the current density was a constant. Okay. And that allows you to do it without really any calculus. I'm going to actually say, let's let the current density be proportional to R squared, which is actually a little more realistic. Oliver Heaviside and people of that time had discovered that the vast majority of the current is really just on the outside edges of the wires, especially when you're talking AC. So in that sense, by putting it proportional to R squared, you're making very little bit going through the center and quite a bit going through the edges. So I'm going to do a problem like that, as well as the problem with the toroid. So anybody have any questions before we get started? Sean, I did ask a question. The other three guys already replied. I have the practice midterm up, and there's a version called Respondus. That's not going to be graded. It's not going to count in your grade in any way. You can still take it. It's got questions, and you can still get a score on it, but it's not going to be contributing to your practice test score. I'm going to have another version up that'll say Respondus video, and that will make sure you can use the video monitoring system. So I need to ask you, do you have a camera, video camera or internet camera connected to your computer?
Yes, I do.
Okay, cool. Just want to make sure. Hopefully whoever's not here, I think I'm missing 2 people, maybe 3. Whoever's not here, hopefully they'll see this in the video and be able to comply with that. So, or at least let me know. There's other ways we can do it, but what we'll plan to do is do it during the actual class meeting time. I'll probably let you, if I decide to go a full 2 hours, let you have a full 2 hours, I'll let you start 45 minutes early or finish 45 minutes late. I think y'all have lab right after that, so you probably don't want to finish 45 minutes late, but I'll give you 45 minutes early if that works for you. If that's going to be a problem, though, let me know. If y'all can't do it early, I know you can't do it late, then I'll just make it sure it's a test that's worthy of 75 minutes, not worthy of 2 hours. Okay. All right. So first off, I'm not going to do the toroid first. I'm going to do the more complex one with the Ampere's law first, and then I'll go back and do the toroid. Toroid is actually pretty straightforward. But like I said, I just took the time to type out this one so you could read it. So let's get started with that. I want to go by sharing my screen, and then I'm going to turn on my iPad, which seems to be working okay so far. Okay, so this is the question, and of course I'm going to do like I normally do, and I'll orient the z-axis along the symmetry axis of this wire. It says consider a long wire carrying a total current I with a radius r and a current density J that is proportional to r squared. I couldn't find out how to put a superscript on that, so I just did the caret symbol. What is the constant of proportionality K and its units? In other words, I'm saying J is equal to some constant times r squared, and I want to know what K is since we are pretending we know big R and I, and I want to know the units as well. What is the magnetic field for R less than big R, and then what is the magnetic field for R greater than big R? So that's the problem that we're trying to solve, and we're going to do it with Ampere's law. Okay, so let's go ahead and get started. I'm going to say this is my solution. I am going to switch to writing, and I'll be writing in blue. So solution. I'm going to go ahead and draw the actual axis system. So what I'm going to say is this right here is the z-axis. And maybe I'll say right here is the y-axis. No, I'll say that's the x-axis. Oh, I can't do it that way. I forgot. Okay. And then I'll say this right here is the y-axis. So now I'll turn it off the automatic, complete the fancy stuff, call that x and call that y. Okay. Now what we have here is a wire carrying the current. And this is where I wanted to draw straight for me. So I should do a little better with that. Oh, that's terrible. Okay, that's making me mad now. So I think I want to delete just that thing if I can. Nope, I just can't do that thing. Why is it doing this? Okay, now nope. So I'm gonna do this, this, and this. Okay, so maybe that helps. All right, now I got another person coming in. That's good. So I'm wasting a lot of time with my OCD here. That's awful, super helpful. So I'm going to go back to my green wire. I'm going to start from this edge. Dang it, there it goes again. And I pushed that button that time. Okay, and now I'm going to do from this edge as well. And what we're going to say is this is a wire carrying a current I. And of course, it has a radius that is from here to here, and that's R. Okay. Now, what I will do is I'm going to imagine a Amperian loop, which I'll make circular. We're doing for R less than big R, by the way. So I'll say an Amperian loop right about here, say, and it has a radius R. Okay. And my hypothesis will be, actually, go back to blue. My hypothesis is that because this I points in the positive z direction, if I wrap my fingers around it with my right hand and my thumb pointing in the direction of the current, then I'd see that it actually points in that phi hat direction. So I'm going to say from symmetry, B is equal to B only a function of R and times the theta hat direction, which I've talked to you about before with, spherical or cylindrical coordinates, or spherical coordinates for that matter. And that's what we're going to use. Again, you don't really have to know the ins and outs of these coordinate systems. I'm just giving you the symbols and you've seen them before. So hopefully that's okay with you, but it makes life a lot easier to express it that way. Remember, basically, if you drew a line from the origin to some point in space, a line parallel to that line would be basically the r hat vector. And if you made sure it pointed that same direction from the origin towards the point, and it was 1 unit line, it would be the r hat vector. And then 90 degrees in front of that, lying in the xy plane, is the theta hat. So that's what I'm actually saying with this. What we know, though, is that Gauss or Ampere's law says the closed integral of B dot dl is equal to mu 0 I enclosed. And this is a case because I made the J a function of distance. You actually need to work out sort of an integral. You can probably figure out some way to do it without integral, but I wanted to show it to you. So I enclosed is going to be equal to the integral of J dot dA, where J is a vector called the current density. It should point in the same direction as the current, and dA would sort of be that little circle that I have in there as an Amperian loop is a good representation of the dA magnitude, but the direction, of course, would be, in this case, I want to say it's exactly parallel to I, because you remember you make the dA vector perpendicular to the actual surface. So what I've conjured is that J in magnitude is supposed to be K times R squared. So I also know that it's in its entirety, it's supposed to come out to I. So I'm going to work out the I part first. So let's say I, which is the current we were given, is equal to the integral of, since the J is pointing in the K hat direction and the dA is pointing in the K hat direction, we're going to say it's K R squared K hat dotted with, again, we're going to do something arbitrary, but you might even say, let's say this is a ring and it's parallel to the xy plane. The actual ring itself is lying in the xy plane, and the dA, of course, is the vector perpendicular to that. So it's going to have a size of 2 pi r dr, and that's going to point in the k hat direction as well. So hopefully I'll recall seeing that, like when we did Coulomb's law and stuff like that. The 2 pi r, we're just imagining it's sort of a circle, and of course the radius, or excuse me, the circumference of the circle is 2 pi r, but we're allowing that r to change from r to r plus dr. So if you laid that out as a rectangle, it would almost look like a rectangle, but it has sort of size like this because the inner radius is, or the inner circumference is a little bit smaller than the outer circumference. And basically you could say if it was a rectangle, it would be 2 pi r wide and dr tall. So that's why I'm saying 2 pi r dr is the area. You can look on my YouTube channel. If you actually compute what it is, it's supposed to be pi parenthesis r plus dr close parenthesis squared minus pi r squared. And what you'll see is if you actually work that out, squaring the r plus dr and carrying out all the polynomial, what you end up getting is some differential terms that have dr to the square power. And of course, if dr is infinitesimally small, dr squared is totally insignificant. So that's why we can actually say 2 pi r dr. Again, if you want to see that, just look on my YouTube channel. I do it. That means I can pull out the 2 pi and the k. So I'll say 2 pi k like this. And that leaves me with r squared dr k hat dot k hat, because the dot product is a linear operator. So you can pull those vectors through the dot product, or those magnitudes scalars through the dot product. And of course, the magnitude of K is 1. The other magnitude is also 1. And the cosine of 0 is 1. So this is just 1. And we're going to integrate. In this case, I'm going to do the whole thing because I'm trying to do part A, which is where I'm determining what the constant is. So I'm going to actually integrate it from R equals 0 to big R. That's why I use this particular I here, because that's the total current that we were told it was carrying. So now I have a fairly easy integral. It's going to be 2 pi times the constant K, which is not related to K at, and I'm thinking I really shouldn't have used that K there now, but anyways, it's not a big deal. The integral of R squared dr is going to be 1/3 R cubed. And of course, if I evaluate that at R, that's 1/3 big R cubed. And if I evaluate it 0, that's going to be 0. So I'm going to just say 1/3 R cubed. So what we get is I is equal to 2 pi K R cubed over 3. So we can now, since I is something we're supposed to know and R is something we're supposed to know, that's what it means when I list it in a problem like that and that, that means we know it, okay? So I'm going to solve for K, and it looks like K will be equal to 3 over 3I, excuse me, over 2 pi R cubed. And you can see from that, it would have units of amps per meter cubed. Okay. Actually, excuse me. Yes. The K should have units of amps per meter cubed. I got to make sure everything's working right, because J actually ultimately has to have units of amps per square meter. And if that's the case, then I'd say amps per square meter is equal to K times R squared. So that would be amps per cubic meter times A per R squared. Yeah, that works. Okay. Any questions on that? So that's the first part. We were able to determine this. I'll just remind you, J is equal to K times R squared, and the units of J have to be amps per square meter. And you can see that that should come out that way. Okay. Now that we got that part, we're going to do the whole thing. We're going to actually determine the magnetic field using our hypothesis up there for R less than R. So let me write down R less than big R.
Aren't we getting amps per meter when we do that?
Oh no, because when you're going to take that J, you're going to multiply it by dA, which has units of meters squared. So when you integrate J times dA, the math works out that it's amps per meter squared times meters squared. So you just get amps out. And so if we look at the K, that's going to be amps per cubic meter. And then the R squared would be amps per meter squared, which is exactly what we want. So yeah, that all works.
Amps per meter cubed times meter squared is equal to amps per meter, right?
No, so the amps per meter squared is what comes out when you actually plug in I and R cubed. So if you plug in I and R cubed, you're going to get amps per cubic meter multiplied by 3 and divided by 2 pi. But then you're going to multiply that by R squared to get the current density. So that's going to reduce 2 of those in the meter cube down to just meters. Yeah, something like that. Actually, let me check that.
All right, if you have K, which is in amps per meter cubed, right?
Right.
So you've got a big cubic chunk, cubic centimeter of copper or whatever, times meter squared, then you'd have per meter.
Oh, yeah, it looks like it might be like meters to the 5th. I don't. So
or meters to the 4th.
If I look at it that way, I can say, let's say amps per meter squared is equal to K times meters squared. So that does suggest meters to the 4th power.
Right. So did we
Oh,
mess
wait
up?
a second, did I? R squared. Oh, remember? Okay, that's
I
exactly
forgot
what
to
happened.
multiply an
catch.
R.
Yeah, did you see this in here? Actually, let me do this. This part right here had an R in it, plus I had an R there. So that should have been an R cubed. Thank you. So yeah, that actually, this is a beautiful example, and I didn't mean it. I'm not trying to claim that, but this is a beautiful example of the value of me asking for the units. I actually was able to, or you guys were actually able to capture an error I made just because we did the units. So let me erase this. And what we're going to see is this quantity right here is not R squared, but in fact R cubed. So I can come in here, I can take that away, and then come back here and put R cubed there, and then shrink it back down. So that looks like R squared times R cubed. So yeah, now it's correct. Thanks. Nice catch. I think that was Nathan I was talking to. Yeah, good catch, bud. So let's continue on. Now we're going to have 2 pi k. And of course, the integral of R cubed is 1/4 R to the 4th. And when I evaluate that at big R, it'll be 1/4 R big R to the 4th. And when I evaluate at 0, it's going to be 0. So I'm just going to put 1/4 R to the 4th here. And now we'll get a correct answer. And it was sort of bothering me a little bit. I kept thinking, but I convinced myself it was okay. So yeah, thanks for sticking to it. So when I get this, I'm going to say, I've got 2 pi k R to the 4th over 4, which obviously that means this 4 will cancel out with this 2 and just leave a 2 down here. So now I can say from this, I can say that I is equal to 2, or excuse me, I is equal to, let's go ahead and solve for, well, no, I'll go ahead and write it out. I is equal to pi k R to the 4th over 2. So that implies that k is equal to 2i over pi R to the 4th. And this is the part that got me in trouble before, but you can now see that the unit of k, the dimension of it, is in fact amps per meter to the 4th power. And now that should work to get a K that has units of amps per meter to the 4th multiplied by meter squared should give you a amps per meter squared, and it does. And then, of course, if you integrate that J dot dA, that's going to give you just a plain amp. So thanks for catching that, guys. Good job. Like to see you paying attention and catching my errors. Next part, we're going to do what I said, which was for R less than big R. And I'm going to use my hypothesis, and I'm going to work on the left-hand side first. And you can see from my Amperian loop up there, the left-hand side is going to be integral of B dot dL. Remember, it's an L for Ampere's law, not an A like it is for Gauss's law. This is going to be integral of B of R times theta hat dotted with the same, in this case, we're actually going to do R d theta, because that's a little bit of arc right along tangential to that little itty bitty red circle. That's going to be R d theta, and that's going to point in the theta hat direction as well. And we'll notice the current does go, if I'm going around in the positive theta direction, that's exactly the direction that the magnetic field should go. So I've got it aligned nicely. Now, this is just going to make, ultimately, you know, the B of R times the R will come out in front, and I get integral of B of R, which is actually just a constant, times R times d theta times theta hat dot theta hat, which becomes my neat little owl. That's one. The B of R and the R, we're actually integrating along a circle of radius R. So those R's are actually constant. So I end up just getting the integral of d theta from 0 to 2 pi. Okay. So ultimately, the left-hand side is just going to be equal to 2 pi R B of R. Okay, and remember, that's what we expect with Ampere's law, just like we expected with Gauss's law and electric field times an area. We're going to expect a arc length times, or some kind of length times a B. Now the right hand side, we've seen how that works out. The right hand side is supposed to be mu 0 I enclosed, but this time we're using R less than R. So we're going to go through the same process that we did when I was computing K. So in this case, it's going to be mu 0. I'm going to ultimately have an integral from R equals 0 to R of, dang it, I hate when it switches to a ratio like that, from a 2 pi K times R cubed dr, and that of course is going to be times a k hat dot k hat. In other words, I'm just taking the same problem we just did in the computation of k, but I just got a different range of integration. So I'm going to get mu 0 times 2 pi k r to the 4th over 4. Okay. And actually, that's supposed to be lowercase r. Sorry about that. I just wrote r to the 4th like a ruler. So that's r to the 4th there. Obviously, that cancels out this 2 and leaves the 2 in the bottom. So things are golden. I can now let left-hand side. Oh, I don't want to do that. I can let left-hand side equals right-hand side. And in this case, it's going to give us 2 pi RB of R is equal to mu 0 I pi, excuse me, R to the 4th over 2. You can see now this is going to cancel out with that and leave a 3 up here. And that's going to suggest that B is going to be equal to, and I'm going to actually do it 2 ways, and let's go on the next page to do it. First, I'm going to put it in terms of the K, which I left off here for some reason. Let me put that K back in there. I just put it right here. Yep, it was there all the time. That's where it was. Okay. So now I've got B of R times mu 0 K pi R. Yeah, that all works. So I'm going to basically divide both sides by 2 pi, and that'll be mu 0 K R cubed, mu 0 K R cubed. The 2 pi's cancel out, or the pi's cancel out, but I end up getting 4 in the bottom. And that would be in the phi hat or theta hat direction. Now, if I go back and plug in what K is, which is part of the reason I solved for K, I can see that B is also going to be equal to mu 0 over 4 times 2I over pi R to the 4th times R cubed. And all of that will be in the theta hat direction, which I can make some cancellations with. Clearly, this 2 is going to cancel out here and leave a 2 down here. And that's about it. So I'm going to say it's mu 0 I over 2 pi big R to the 4th times R cubed in the theta hat direction. Hopefully I didn't make any algebra simplification mistakes there. But there's 2 values. And technically this second one is the one you would need to turn in, because I didn't give you K, right? In the question, I gave you I gave you big R, and I told you how we could compute J in terms of K, but I didn't really give you those. So you really shouldn't have a K in your final answer. And you look at this looks just like mu 0 I over 2 pi R, what you normally get for a long straight line. But in this case, in order to get that 1/r dependence, the little r and the big R have to cancel out, but they can't because they're two different things. So we actually get B being proportional to R to the third power as long as we're inside of the actual wire. So that's a lot stronger. When you do the one in the book, that's going to be a constant J, and you'll end up getting that the magnetic field is proportional to R inside the wire. Here it's proportional to R cubed. So now we're going to do the next part, which is finding it for R greater than R. So for R, anybody have any questions before I move on to, by the way? Anybody have any questions on this one before I move on? Anything you didn't understand? That 3 looks really bad to me. Sorry. So no questions? All right. Well, let's slap this on now. So left-hand side, it's the integral of B dot dl, which again is the integral of B of R theta hat dotted with R d theta, theta hat. Okay. Of course, this is just going to be 2 pi R B of R. So we've got that. The left hand or the right hand side is going to be mu 0 I enclosed, but here we did give us a total. We did give you the total current I, and it's matching the right hand rule, so we don't have to make it negative. So I'm just going to write it. It's just mu 0 I, easy peasy. What we see, left hand side equals right hand side. That gives me 2 pi R B of R is equal to mu 0 I, which lo and behold is just what you expect, hopefully. B is equal to mu 0 I over 2 pi R in the theta hat direction, which is exactly what we got for an infinitely long wire. Again, in physics, infinitely long just means at least a factor of 10 closer to the wire than you are to its end. Obviously, a factor of 100 would be even better. So I can make a graph of this now, and that's what I'm going to do. I'm going to make a graph, and it's going to be a graph of the magnetic field versus the distance R, and I'll put big R right here. I don't know if you guys are familiar with the R cubed function, but basically it looks like this. Okay. In other words, if you drew the whole thing, it would actually look a little bit like the tangent curve, like that or something. But in this case, that quantity right there, we go back and look at replacing little r with r, you're going to get, looking down there at the bottom, big R to the fourth power or to the third power over little r over big R to the fourth power. Those are going to cancel out and just leave mu 0 I over 2 pi big R. So this is going to be mu 0 I over 2 pi times big R. Now, this is a little inconvenient, so I'm going to take that graph away. Okay, so that's what happens for less than R. But when you go to bigger than R, it's just going to fall off like 1 over R squared. So it'll go gradually like this. So that's what the magnetic field strength looks like as a function of R. Basically, it's going to rapidly increase until you get to big R, then it's just going to fall off just like a regular wire does, current carrying wire. So any questions on that? Quite easily done. That's not the Latin. That's the version I like. Okay, so now, does anybody have any questions on that? Because I'm getting ready to do another quick Ampere's law, but I'm going to do it with a toroid, which is basically, imagine a solenoid as like a long cigar, say. So if you had a long cigar and you smoothly wrap the wires around, you get something more like a nice solenoid, where you literally have one loop around and then it's just a little bit over, maybe one diameter over, and then there's a second loop, and then it's one diameter farther to the right again, so it's another loop, another loop, another loop. And now once you take that, you can pull the cigar out and you take the thing and shape it into a ring, so it literally looks like a donut. Okay, that's what a torus or toroid is. And in fact, if you've played games like Maelstrom, and we used to play Asteroids, that actually, believe it or not, is the I want to say topology of an actual asteroid game is the surface of a donut. So I'm going to take a little fun time and show you that real quick. Does anyone have any questions on this application of Ampere's law, though? Anything in this that threw you or anything? All right. Looks like you got it then. Okay. So here's our first proof. So if you've ever played Asteroids or any game like that, you know that basically you have a screen that's sort of rectangular, like so. And you know that, like, if your ship goes out, let's say out this side like that, okay, it immediately appears on the opposite side like that. So that shows you that the left-hand side is equal to the right-hand side. So from that, we can say, okay, I'm going to draw a little line back here, and that's where they meet. Actually, I don't like that. Okay, and here's the bottom side, and that's where they meet. I wish I could make that a little smaller. Let's see if I can. And center it up a little bit. Okay, I'll make it a little bit bigger. That's good. So, whoa, nilly. So now I'm going to draw that, and that's your actual screen. You just can't see, for instance, generally you wouldn't be able to see this part right here, but you definitely could see this part right here running into there. So that's what we've shown with that, is that the left-hand side and the right-hand side are in fact equal. And the way we did that was just wrap it around till they touch each other. Okay. Now, the other thing is, if you're playing Asteroids and one of your ships goes off here, like this way, then it immediately appears over here. So that means the top is equal to the bottom. So that means this part has to touch this part, which forces you to ultimately draw this shape. So what I'm going to do is I'll have to make it a bit smaller here, but I can draw this shape. I can draw this shape. And then I can draw this shape. And then I can draw this shape. So basically, by locking that in there, you now have a seam that goes along the back, which is supposed to be represented sort of by this. And that comes around to the front, which goes like this. So that's actually how we say that this is actually a donut. because the only way it couldn't, I mean, the only way you can have something going out the top and coming back in the bottom or vice versa is if the top equals the bottom. And if it goes out the right and comes in the left has to equal the right. So we end up making a donut. Donut. All right, now that we've got that done, let's look at an actual example of a toroid, and I'm going to work with Gauss's law, or excuse me, with Ampere's law, and compute the actual magnetic field inside of it. So what we're going to do is we're going to imagine the solenoid has a fairly small diameter, but it's going to be bowed into a circle that has a pretty significant size. So what we're really imagining here is a bunch of wires. There's a current coming out, there's a current coming out, there's a current coming out, current coming out, current coming out, 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 on forever like that, okay, around the whole circle. And then inside, there's a current going in, current going in, current going in, current going in, which has the same number of wires as the ones going out, because they're literally leading to it. So the current's like coming out at the, what we sort of call the top of the solenoid, the current's coming out, and then it loops out in front of the page and then goes back down and goes behind the page and scoots down a little bit. So if you actually grab, say those currents pointing up, you'd see that your hand goes like this, and that's going to force your magnetic field lines to go around this way. Okay. Which means I am going to say that my positive x-axis is right here. And my positive y-axis is right here. Okay. So then I can assume, now I'm assuming the current in the wire is I, and I'm assuming the total number of turns is N. And I'm assuming also that the radius from here to the midline is big R. Okay. So now I'll write solution. First, I make a hypothesis about my magnetic field. That hypothesis is that B, the magnetic field, is equal to B, a function of R, say, which is the radial distance outward, again times the theta hat direction. Okay. Now my little arc length around this Amperian loop, which I showed this as magnetic field, but the Amperian loop would do the same thing. That's an Amperian loop. So with that Amperian loop, that tells me that my DL should be equal to, I'm going to make it out a distance big R times d theta in the theta hat direction. So now I can say left-hand side, closed integral, B dot DL is equal to integral B of R theta hat dotted with big R d theta theta hat, which is equal to B of big R times big R times the integral d theta times theta hat dot theta hat, which I'll literally take the time to do this just so I can draw this little owl. Okay, that's going to be 1 again. So ultimately I get 2 pi R times B of R. And that R just happens to be the size of the center of the radius of the solenoid, and it's not going to vary very much. So you just leave it there, right? Now the right hand side is actually really easy. You realize all the currents you've got enclosed there are really just the ones going into the page, and the ones going into the page, right, require the thing to go around in a clockwise direction, and that's exactly the way we went. So I've got a positive current, but instead of having I, I've got N times I. So mu zero I enclosed is just mu zero N times I. So I can now write left-hand side equals right-hand side. And that will give me 2 pi r times b of r is equal to mu zero N times I, or b is equal to mu zero N I over 2 pi r theta hat. Okay, and if you'll notice in your book, this result, I'm looking at right now just to make sure, this result is one of the equations that is numbered, if I remember correctly. Okay, that's that one. Might be the next page. Yeah, so it's section 28.5. I'm checking in the book real quick just to make sure. Yeah, they got the solenoid formula. B is equal to mu zero lowercase n times I. That's equation 28.4. So what that means is, hey, that equation's in the book. You can use that. If I ask you a question, unless I explicitly say, hey, you got to show me, prove that this is that using Ampere's law, then no, you don't have to do that. You just have to apply the formula. Mu zero lowercase n times I is the magnetic field for a solenoid. And then for a toroid, they said it's mu zero capital N times I over 2 pi r. They did that in an example. Let's see. It looks like they never labeled that one. So if I ask you that one, then you're expected to have to derive it. Okay. So I'll show you that real quick. Let's stop sharing the screen for just a second. And I'll start sharing the screen, a different screen now. So you can see up here is where we did the solenoid, which I did last time. Okay, you can see the solenoid like that. And that gave you this formula, mu zero lowercase n, which remember is the total number of turns divided by the total length, times I. That's numbered. So that's an equation you're allowed to put on your equation sheet. And if I ask you to calculate the magnetic field, say at the center of a solenoid, you're perfectly free to go ahead and just take that equation and plug and chug. However, when they do a toroid, like I just did, that's an example. They work it out, but look, no number. So if I ask you for a toroid, then you're going to have to do the derivation. Any questions on that? I noticed I did the abuse of art first because I like doing the hard way first and then doing the easy way so you feel better about it. But here was the law of abuse of art, for instance. Remember, your book does it like this, but I specified a little bit more. I'm going to go ahead and write these things down now that they're sort of fresh in my mind. B for a solenoid was equal to mu zero lowercase n times I, where lowercase n is equal to the n over big L. B for a wire is equal to mu zero I over 2 pi r. And B for a toroid, which I'll say B sub TOR, is actually mu zero n I over 2 pi r. So these are all equations you can use. Well, that bottom one you can, as I just showed you, but they are equations you can refer to. I don't care when you're doing your homeworks. If you're just plugging and chugging these formulas, fine. But I would take the time to try to derive the solenoid problem. Now, the other thing is the law of abuse of art. Actually, let's take that last one out. That big N is the one that's in here. Now, the law of abuse of art, I said, was dB is equal to mu zero I over 4 pi. And then I said dL cross RP minus R dl over the magnitude of RP minus R dl to the third power. Okay. And remember, it's not a 1 over R cubed law. It's still a 1 over R squared law. But in order to get the magnitude of the 1 over R squared law, you actually have to take, or excuse me, to get the direction, you multiply it by a unit vector. To make a unit vector, you take a regular vector and divide it by the magnitude. So I stuck the regular vector in the top and then divided by an extra R at the bottom. So now I'll go ahead and stop sharing this and show you what I wrote down on my iPad. So now I just gave you a refresher of what the equations were, and I'm going to remind you here, this one is not numbered. So any questions on that? I don't know how I just changed the thickness of my font, but I did. Kind of excited about it. It looks really nice. Makes my handwriting not look like I got, I don't know, Alzheimer's or Parkinson's or something. But anyways, all right. Any questions about any of that stuff, guys? I say guys. Actually, we are all guys this time. All right. So we'll go on. The next chapter we're doing, I'm going to stop sharing my screen for just a second. The next chapter we're going into is chapter 29. We have now finished chapter 28. We actually sort of finished it already, but I'd already made the homeworks due not this past Sunday. So you've still got more time to do your homeworks. We've done the law of Biot-Savart for very specific types of sides like this, where basically you get 1 over mu 0 I over 2R for a whole circle. And then, of course, if you only have a quarter, then you got to divide it by 4. So you get an 8 down here instead of a 2. So that's the trick. And basically all the currents that run towards the origin are away from the origin. They're radial, so they don't contribute at all to the magnetic fields. But the ones that run tangential to a circle always give you, according to the right-hand rule, a magnetic field at the origin. So we did all that stuff. Now I'm going to jump to electromagnetic induction, specifically something called Faraday's law. So Faraday basically had an experiment sort of like this, where he had a solenoid. So there's a good picture of a solenoid. Those are a bunch of little wires wrapped around some plastic over here. So, and they're varnished. They have a painting like lacquer material over top of them, so that the current can't leak out through the sides and go into the wire next to it. That's what that solenoid is. And then they've got one end of the solenoid connected to the positive side of this galvanometer and one end connected to the negative side. And what Faraday did was he would connect something like this. He actually had it on a ring of metal. In fact, you can see the ring of metal. They've got it like in a museum for the Royal Society or whatever. But basically what he did was he noticed if he had a wire around a magnet, nothing happened. But what he noticed is when he closed the switch to let the current run through, the galvanometer type thing that he had would sort of swing a little bit and then just stop. And then when he turned it off, it'd swing a little bit and stop. In fact, it swung a little bit the opposite direction. So he realized, oh, wait a second, it's not the presence of a magnetic field that creates a current. It's the more related to the changing of the magnetic field that creates a current. And that put him on the idea of thinking about a change in not only a magnetic field, but something we now define as flux. So in order to do Ampere's law, we actually have to use flux. But good news is we've already discussed flux. It's just now we're going to do it in terms of a magnetic field. So this is sort of like Faraday's experiment, where basically you'd see this battery right here. Conventionally, that would mean positive charges flow out here, and then they go around this, around this, around this, around this. And of course, by saying around that, that means the magnetic field through this iron wire would be counterclockwise here, or through this iron ring. And since it's iron, there would be some ability for the magnetic field to stay in here and would go all the way across here. Okay. Well, it turns out, this is Lenz's part of Ampere's law. Lenz's law, your book says it, so I definitely write it down several times. Lenz's law tells you that whenever a magnetic flux changes, the induced EMF or the induced current will act in a way to oppose the change of the flux. It doesn't oppose the flux, it opposes the change in flux. So when this wire first starts carrying current, it's creating a magnetic field through here where there wasn't one before. And of course, that magnetic field would be going counterclockwise as we're looking at it now. So what would happen is this right-hand wire that's connected to the galvanometer and doesn't have any power source, that would try to create a magnetic field to fight that magnetic field because it used to not have one, now it has one. So the flux is actually increasing. It's going to try to decrease it by creating a magnetic field pointing in the opposite direction. Now, if the magnetic field pointed in the opposite direction, that means your fingers have to go behind that top wire right here and down through the green thing like this. Well, if you're doing this with your right hand, you stick your your right thumb out, you'll see that that current is actually coming from the left side of the galvanometer and going in the right side of the galvanometer, which I would generally tend to think of as the positive one. So this red needle would deflect to the right. Now, once it got there, basically equilibrium would be established. The current would be running through there. It would create a magnetic field, and that magnetic field would stay there and it wouldn't change until the battery started to wear out or something. So it would drop back to zero. Now, when you take the switch and open it back up, then what happens is the current goes off. And what this galvanometer wire remembers is, hey, there used to be this magnetic field going up through this way, and now it's starting to decrease. The flux is decreasing, so I'm going to try to increase that flux by this time creating a magnetic field going in the counterclockwise direction. Well, if you stick your right hand fingers behind that top wire or that bottom wire, either one doesn't matter. If you stick it upwards, then you see that when you're grabbing that bottom wire, your right thumb points to the right. So the current's going to go around this way and go in the left side. That's going to indicate that it'll deflect to the left. So that's what actually Faraday found. He didn't know it mathematically, but he figured it out so well and figured all of it out so well that James Clerk Maxwell could just come along, read his notes, and translate it into mathematics because the guy described everything so well. It was pretty obvious what he was saying mathematically. So Maxwell just copies all that down and actually finds an error in Ampere's law and fixes that, and then writes it in quaternion form, and he writes it also in potential form, which is both cases are really ugly. And basically he died without the respect of his peers, even though he'd done a great thing. For starters, the respect of his peers was lost because he was a second wrangler in Cambridge at that time. And maybe even still, they had a wrangler test at the end of your 4 years of college. And it was a test that everybody took that covered physics and mathematics and stuff like that. And you take that test, and it's like maybe an 8-hour test, sort of like the GRE is nowadays, but probably much more rigorous. And specifically because it's nothing but math and science. And you answer those questions, and they grade them, and then they take the grades and they post them in order of greatest to lowest on the walls with your name next to it so everybody can see it. And the first person, the highest number up there, is the person that got the best score, and they call him the wrangler. And the second person is called the second wrangler, and Maxwell came in second. Maxwell went on to do great things. He was the first one to prove what the rings of Saturn were. He was able to make statistics about atoms. He was able to basically unite magnetism and electricity in 4 equations that pretty much cover almost everything you need to know nowadays for E&M, for electricity and magnetism. He predicted the existence of electromagnetic waves. He invented our color system, the RGB color system that we use in computer programming and stuff. All that was done by him. Okay. but he wrote these Maxwell's equations in a really difficult form, and a lot of people just didn't know quaternions. Hamilton, a different Hamilton, but a Hamilton, a famous mathematician, had created quaternions. He thought it was his greatest thing. In fact, he's even got the multiplication rules for the quaternion on his tombstone, but they turn out to be kind of crappy, not that helpful. But either way, he had written them that way, and a guy by the name of Oliver Oliver Heaviside, and some other guys, they call it Maxwellians. They got into Maxwell's equations, and more or less Oliver Heaviside and a guy, I think it's Stephen Gibbs, the guy that's from Gibbs Free Energy in America, those two people simultaneously invented what we know of as vector calculus, in trying to represent Maxwell's equations in a new light, and they made it. And that's ultimately what got Maxwell's equations known, is because they put them in vector equations and vector calculus, and it worked a little better. So anyways, that's how it happened. And by that time, Maxwell had already died. He died at a very young age, I think in his upper 30s or lower 40s, from stomach cancer, just like his mother. Which is really sad, a great loss. But by the time Einstein comes along, Einstein knows Maxwell's the bomb. Everybody figured out that Maxwell's the bomb. And in fact, Maxwell's equations are already correct with special relativity. And that's the impetus that gave Einstein the idea that the laws of physics were messed up. Nobody thought the laws of physics had anything left to do with them. They were, if you survey most of the scientists at the time, right after Maxwell, say the 1860s, 1870s, up to early 1900, or maybe just shy of the 1900s, they would probably tell you, well, we've figured out everything. It's just a matter of checking that all the equations work, even to like the third decimal place instead of the second. But Einstein saw not only did he hit a target that no one else could hit, he saw a target that no one else saw and then hit the target. And he introduced special relativity, and the reason why he named it on the electrodynamics of continuous matter or something like that, mainly talking about the electrodynamics part, was because Maxwell's equations gave too many paradoxes unless the speed of light was a constant independent of the motion of the source or the motion of the observer. And lo and behold, Maxwell's equations were already correct, and Einstein just had to figure out why. So anyways, with that said, I'm going to go ahead and tell you what this says here. I've given you sort of a intro to it. I want you to be able to do questions like this. Okay. I want you to be able to solve questions like this. Let me show you an example. I am going to stop sharing my screen now and start sharing another screen. These are problems where you're using Lenz's law. So you imagine a magnet being thrust through a ring of wire, and then magnets drop through a ring of wire, or other things. Your book will have a bunch of examples. And that's one of the most fundamental laws of physics, is Lenz's law and Faraday's law. So you definitely want to be able to do that. What I'm going to do now is give you an example and show you how to work it out, just like I just did with that particular setup that Faraday was using. So let's imagine a scenario like this. We're going to have a bar magnet whose north pole is down and whose south pole is up, like that. Okay. And it's going to be a long way away from a loop of wire. Whoa, Nelly. Hey, man, you weren't supposed to erase the whole thing. Come on. Okay, so now I'm going to bring this over here. I'm going to bring this over to here. And it's going to be connected to a galvanometer, say. Okay. Now, right now, the magnetic fields for this magnet, remember I told you magnetic fields behave like old people. And that's just a disrespectful but cute metaphor. Okay. They leave the north and enter the south. That's what I mean by that. So this is what the magnetic fields look like from this magnet. And as you can see, when it's really far away, there's no magnetic flux. And just for the record, the definition of magnetic flux is phi
B, or phi sub B, is equal to the integral of B dot dA. Notice that looks just like Gauss's law, except it's not a closed integral. We usually put the closed circle on there to indicate it's for a closed surface. This is just the integral through any surface. And we define, in fact, the surface to be, you can imagine, for instance, a loop of wire as if it exists in one plane. And then you take that wire and you dip it in a solution of water, a little bit of dish detergent, and a little bit of glycerin. And you probably know what I'm referring to now. That is bubble solution. If you want to make your own bubbles for your child, that's the way you do it. You take water, you take Dove dish detergent, some liquid detergent, in other words, and a little bit of glycerin, and put that together. And then when you pull the liquid out, it'll actually stick to the plane of that loop of wire. Now, if you take that loop of wire and pull it left or right, the bubble surface will go from flat to like bulged out and all these cool shapes. Well, all of those shapes that could be sort of encapsulated by that wire, all those possible shapes are the surface we're talking about. So that's what we mean when we're calculating a flux. The surface is through any of those bubble shapes that could form around that circle. You usually think of just a flat one because that's easiest, but all the bubble shapes are in there. So as this thing gets closer and closer, so this is T1 and this is T2, the flux, which is only dependent on the magnitude of B going through the loop, the area of the loop, and the relative orientation, i.e. the dot product of B and the A vector, which we know is perpendicular to the loop. So do you think the flux is increasing or decreasing from T1 to T2?
Increasing.
Yes, flux is increasing. That's the first goal to solving these problems. You first got to decide, is the flux increasing or decreasing? It's increasing. So what that means is I/E induced is going to try to oppose the change, which means it's going to try to decrease the flux.
Okay. The only tools it has at its disposal is it's an electric field. I mean, it can make voltage. And since it can make a voltage, it can make a current. And since it can make a current, it can make a magnetic field. So all it can do is make a magnetic field. In this case, that we're trying to actually decrease the flux, we're going to make a magnetic field, hopefully, that points in the opposite direction of the magnetic field that's currently being exposed to. I got to write this word a little better. Not a lot better, evidently, but okay. So in this case, the magnetic field lines, as we see, are pointing down. So nu B is down. So I induced is going to point up. Okay. So with I induced pointing up, which way does the current in the wire have to go? So let's consider for concreteness. Look at this little piece right here. Should the current go to the right or to the left? What'd you say, counterclockwise?
Yes.
Okay. Yeah, I think that's right. If you look from above, that's counterclockwise. I assumed you were thinking above. So yeah, it's basically equivalent to the I induced going that way, because you see, if I grab that wire with my right hand, my thumb pointing that way, the magnetic field points up in the middle. And that's exactly what we want. So I induced will be in that direction. And that's how we use Lenz's law. Now, let me show you what Faraday's law is. Faraday's law, I really got to figure out how to change this font back. I don't like it this big. I kind of like it because you have to see better, but still. So Faraday's law says
the electromotive force induced is equal to negative. I'm leaving a space here for a good reason. You'll see in a second, but it's negative d phi b over dt. Okay. So phi b remembers the flux that I told you, and it's equal to the negative of the time derivative of that flux. Now, if you have one loop of wire, this is your formula, but if you have n loops of wire, then that's your formula. So that's why I left that big space. Now, this part right here, we often attribute to Lenz's law. And that's the one where basically it says an induced current or an induced EMF will be created such that it opposes the change in flux. And actually, it turns out if the other way was true, that it actually just opposed the flux, that would be sort of equivalent to making a perpetual motion machine. It's literally like making energy out of energy. So E induced / I induced will create a magnetic field to oppose the change in flux. That's Lenz's law. So if you're asked for a voltage, you can use this formula and throw the negative away. But if you're asked to take this equation and plug it in another equation, you need to keep that negative in there. Okay. Now, the other thing about the E induced, if you talk about going around a complete circle, then that is E dot dl, which is really our voltage. Okay. So if we go to convert Faraday's law to a differential equation, we start by introducing this on the left-hand side equals negative d by dt of the integral of b dot dA on the right-hand side. And then you just use sort of the generalized Green's theorem, and you'll get basically Faraday's law in differential equation form. Just something to mention to you, not anything you got to do with that or anything. So that is an introduction to Faraday's law. I've got some time left, so let's go ahead and work an example. So let's imagine for a second that actually, let's start with that same setup we had a second ago. We're going to have a north pole here, a south pole here, and we're going to have a loop of wire. Like this. And in fact, I've got to show that that's not there at all. So we have a loop of wire, and then sometime later, that magnet's going to fall all the way down here. And in fact, we can see the magnetic field lines are going straight through like this. So this is T1 and this is T2. So from T1 to T2, what is the flux doing? Is it increasing or decreasing?
Decreasing.
Decreasing. Very good. The answer is decreasing. So see if you guys can figure out what direction the current is going to go in that wire that's sticking out the front. So the flux is decreasing. According to Lenz's law, a current will be induced to oppose that change. In other words, a current's going to be induced to try to increase the flux. So that current in the front part of the wire, the part that's closest to us in front of the magnet, which direction will current be going in that piece? To the right or to the left?
Clockwise.
Yes, as seen from above, yes, clockwise. And the reason why is if you take that wire with your right thumb pointing to the left, put your fingers through the middle, you see your fingers are pointing down. That's the same direction as the magnetic field is in T1. And in T2, the magnetic field's essentially gone. So yeah, you want to try to restore it by putting a magnetic field downward. So yes, the I induced will be clockwise as seen from above. Okay. And what would that flux be? Well, that's where things get a little dicey. So let's go ahead and now that I've shown you another example like this, I'm going to line this off and I'm going to remind you that E induced, which is, by the way, is a voltage. And this N is not always here. Okay, it's only there when you got multiple wires. But by saying it is a voltage, that means E induced can also be given by I times R. Okay, in other words, it's part of Ohm's law. So they don't always ask you for voltage. Sometimes they ask you for the current, but they got to give you the resistance if that's the case. So let's imagine this neat little scenario. I've got basically a fairly uniform magnetic field that is pointing into the page like so. Okay. And I've got basically, let's say, some lawnmower handle that's made out of course, metal. Okay. And across that metal, I have a piece of rebar that's just sitting like there, but it's moving with a velocity v. And this initial distance right here is x0, so that in fact you can think of this as the x-axis. Okay. So I'm going to say that this length right here from here to here is L. Okay. Can you tell me what the area is now? Notice the rebar and the lawnmower handle is making a very tall, thin rectangle. That's the area I'm talking about. Can you tell me how to calculate that area? Would y'all agree it is L times x0?
Yes.
Okay. So the flux, at least its magnitude currently, is just, if I call this magnitude over here B, it's just going to be B times L times x0. Now, can you tell me what x, the position of the rebar, is as a function of time? I've shown you what it is at t equals 0. I've showed you enough to figure out the rest. Can y'all tell me what x of t would be?
It's V times T.
What is it at t equals 0 though?
Whatever X initial is.
Yeah, so you're right, x0 plus v times t. Right? So this is at t equals 0, but phi of t is going to be b times L times x of t. Would y'all agree with that? Because at any time t, the width of the rectangle is going to be that x of t that we just wrote, x as a function of t, and the height's going to be L. So do you see that that's the
flux as a function of time? I'm going to hope you do, and you're just tired or something. So
What that tells us now is I can calculate the magnitude of the induced voltage by dropping the negative sign. And of course, this is an n equal 1 scenario. So it's going to be d by dt of b times L times x of t. Well, that's going to be b times L times d by dt of x0 plus vt. So we get ultimately that it's b times L. What is d by dt of x0 plus vt?
V.
Yep. And I'm going to write it sort of like a nu, so we won't confuse it for voltage. But that's it. That's actually it. And your book's even going to go as far as using that to suggest if you have an airplane wing of length L going through the Earth's magnetic field B with a velocity V, then that can actually count as an actual induced voltage between the tips of the airplane wings. Okay. So this is this is actually an equation that will have a number by it. So you can use it. You don't have to derive it every time, but this is enough to get you started on chapter 29. So anybody have any questions on that? I don't think the homework is due on that chapter 29 stuff this Sunday. I think it's a little bit later. If not, I'm definitely going to move it at least till Thursday or Wednesday of next week. Let me check real quick. See, October 24th and October 31st. That's a long way away. Okay, that's good. That gives me plenty of time because we're only on the 13th now. So I'm going to make them both the 31st instead of, or both the 24th instead of the 31st, because you should have it done by then. All right. So you folks are free to go. I'll wait for the last of you to leave. Other than that, you're free to go. Robert or AJ, y'all have any questions? All right. Well, I guess I'll let you guys go then. I've now changed the homework date for chapters 29 conceptual and chapter 29 homework. They're now both the 24th. So hopefully that'll help you guys. I'm going to go ahead and stop sharing and say goodbye. Bye.